So, welcome to Lab 4 in Physics, where we talk about the concept of an oscillating spring. So, the purpose of this lab is to create an experimental model of an oscillating spring to analyze the motion of a spring mass system in which the spring swings in an arc. This experiment uses the energy principle and Newton's second law, which helps deepen the understanding of those concepts throughout the experiment. So the fundamental concepts we're working with are the energy principle, in which a system's change in energy is equal to the work done on the system plus the heat transferred to or from the surroundings. In this case, the system's total energy remains at zero, showing this principle in action. We also use Newton's second law, as the change in momentum is proportional to the net force applied, showing the principle of Newton's second law, and F net equals delta P over delta T. So here are the equations. The F net is the spring force plus the gravitational energy, and then the delta energy of the system is the work of the surroundings plus Q. So in our experiment, the system is mass, spring, and earth, and the surroundings are nothing. The initial conditions are a time of 0.7 seconds, a position of negative 0.049 meters and negative 0.71 in the x and y direction, a velocity of 0, an initial spring length of 0.7 meters, and then a mass of 0.402 kilograms. And the lab showed how an oscillating spring follows the energy principle. So the procedure is to upload a video and a tracker to create an observed model and then import data into a sheet. Then using the starter code, we can plug in the values from equations and then also import the sheet to get the required data. So for our tracker model, you can see we marked where the spring would oscillate, and we get two curve graphs for the positions. And then all of the data we're given can be used for our calculations and then also our Google Sheet that is imported into the code. So to solve for K that we need in the code, we can use the spring stiffness. K is the spring stiffness. We can use the equation T squared equals 4 pi squared m over K, and then we manipulate this to solve for K, in which we get 6.869 newtons per meter. And then for LO, which is the relaxed spring length, L naught, we use F net equals negative K times L minus LO times L hat plus mg y hat. So we can rearrange this to solve for L naught, and we get 0.12646 meters. So in the code, we change quite a bit. At first, we can put in all of our initial conditions, which we got from the calculations we just did, and then additionally we edit the steps to put in the equations that we're using. So for example, F spring, we put in the equation to find that, and then once we update our code, we produce our models. So as you can see, we have the X position versus time and then the Y position versus time. So the experiment does differ from the model, but they have like similar oscillating waves. It's just also offset a little based on the time it started at. Some sources of error that could cause this offsetting is that in everyday life, the surroundings interfere with the system, so there would be work done by the surroundings. And then also while tracking the object on tracker, there might be slight discrepancies in where the tracking point was placed. So what does it mean? Does it satisfy the energy principle? It definitely does satisfy the energy principle. As you can see, the change in energy of the system equals 0, which is what is required to satisfy the energy principle. There are no external forces since we isolated our system. So as shown by the energy graph, the delta E or yellow line is 0 because the delta U of gravity and the delta U of the spring are inverse and always sum to 0. And then, so the oscillation period examinations, as you can see, we have our calculations. So we find the average time it takes to complete one oscillation, and then we plug that to equation to get K equals 5.987 in the X direction and then 6.869 in the Y direction. So the oscillation periods in the X and Y direction differ, showing that the different directions affect the oscillation period, which would change both the constant spring and the graph. Thank you.